Yeah.
So we can start, sir.
Yes. So can you able to see my screen?
Yes, sir, it's visible,
Yes, sir.
sir.
Yes, sir.
So what was your title? Project title?
Sir,
The method of less power, high performance, and area efficiency decoder design.
So the method of low power, high performance.
area efficient
Area efficient.
address decoder design.
Yeah, address decoders. So for SRAM, okay. So now we are doing our project in a VLSI. So we have to know that VLSI mainly depends upon the three factors. Okay. So that is a area. The next is a power and
Delay.
delay. So what is the area? So all these three factors, okay, has to be reduced. Has to be reduced. Okay. So day by day it has to be reduced and it is going to be reducing. Okay, got it. Suppose like when you just observe the ancient computer, it was like a room size. Okay, but now it is like a means like we can handle it in a pocket. Okay, so that's why area is getting reducing, power is getting reducing, and delay is also getting reducing. Okay, so area in the sense the chip size. When IC size is getting reduced, then automatically the gadget or device size will get reduced. Okay, then comes power consumption. So what about power consumption? If your power consumption is getting reduced, then only you will be having a good battery backup. Okay, got it. So then next comes delay. So if any device is there, it is giving delay. Like suppose I am just clicking on that some icon or something on my laptop or my phone. Okay, but after half an hour it is getting opening. Some then what is the use of that? Okay, so it is means like no one buy that
Lagging,
device.
lagging, sir.
Yeah,
It
hello.
means lag, right, sir?
Yeah, lag. Okay, so when
Okay,
it
sir.
is lagging, so then no one will buy that device, is it? So for that purpose, delay should be reduced. Means all these three factors, if they are going to reduce, then only we can make a perfect IC. Got it? So delay is also one of the factor. So opposite of delay, so sometimes it is like speed efficient. Sorry, speed efficient. Okay, it is also called sometimes speed efficient. Now in our project, so if you can see the title, the method of low power high performance. Got it. So it is given low power means it is consuming low power consumption. Then next high performance. High performance is nothing but it comes about the speed. and then next area. Okay, area efficient. So when high performance will come, so at that time what we will do, we will multiply our power, whatever the power we got from that circuit, with delay. Okay, so high performance. Got it? So if this is getting reduced, okay, then it is having high performance. Okay, so like means like we need to take any other previous one. Suppose this is one high performance one, and the previous one is something high performance two. So same thing we are doing, power into delay. Okay, so now here there is something like 15, and here there is a 12. So which one is reducing? 12 is reducing. So we can say now whatever I have designed, okay, so I see, so it is having high performance, like that. Got it? So the next, now what we are designing, we are designing address decoders. Okay, and for what purpose we are designing that address decoders? Okay, for that SRAM is nothing but a memory. Okay, so nothing but one of the application is there. Okay, so that is called SRAM. SRAM is an application. For that application I need address decoders. Okay, so what is that address decoders? Now we need to know about that. Okay, so we are designing this address decoders. Designing in the sense we are designing the circuit for this. Okay, so now how you are designing the circuit, that is the main factor. Okay, so there are like in previous one, the address decoders. Okay, so decoder is nothing but, you can say, what is a decoder, you know? Do you know a decoder?
So encoder decoder, yes, sir.
Yeah,
We
encoder,
had.
decoder. Yes, yes. See, it is an electronic uh, circuit. Okay, it is an electronic circuit where the input is like n and output is 2 power n. Okay, so this is a decoder, and encoder is nothing but opposite. 2 power n is the input and n is the output.
N is the output.
Yeah, so in previous one, like there are 14 transistor and 15 transistor decoder circuit. Decoder circuit. Okay, 14 transistor and 15 transistor. Okay, so what is a transistor? So see, if whatever in the VLSI, so these are designed with the transistors. So what are the transistors are called? MOSFETs. Okay, so might be we have learned in the EDC is it the subject, electronic devices, EDC, I think so, electronic devices circuits. Okay, so in that we learned about the transistor, BJTs, FETs, and all those things. Okay, so BJTs are the current control devices, so we won't use that. So voltage control devices are using in the VLSI field. Okay, so that is the MOSFETs. Okay, got it. So in that MOSFET we call it as a CMOS, complementary metal oxide semiconductor. Okay, so these transistors we are using. So 14 transistor and 15 transistor we have used in the previous, and decoders we have designed a decoder circuit with that. Okay, the next thing, now in the proposed one we are designing a you can say 12 transistor GDI decoder. Okay, decoder circuit. Now with this itself, okay, with this itself, this is just a I think this is 2 to 4 decoder. Here also this is a 2 to 4 decoder, means 2 input and 4 output. So now how it is used, 2 to 4 decoder, how it is used in a SRAM. or a memory. Okay, suppose this is a memory where I am having a 16 blocks. So this is called 0001. 1 second, we'll write like this. 0000. Hope it is visible to you. Okay, zero zero
Yes, sir.
zero one 0010. This is 2, means 0010 is nothing but 2 in a decimal.
Yes, sir.
0100, 0101, 0110, 0111. Then next 1000, 1001, 1010. Then next 1011, 1100, 1101, 1110, 1111. Okay, so starting from 0 and ending at 15. Now address decoder. So decoder is something like this. 2 to 4 decoder. So here there are only 2 inputs and 4 outputs which are going like this. Okay, the same thing it is happening. See, this is called row. Okay, now if we are coming from vertically, so this is called column. Okay, so again one decoder we will use here, 2 to 4. Okay, then next 1, 2, 3, 4, and 2 inputs here. Okay, 2 inputs. Now suppose I have given an input, something I want to fetch the data from the these fold, these block or these address I can say. Okay, so what I will give, so 01, I will give input here 01. Okay, and then next 10 I will give here. Okay, so there are 4 outputs you can see. Okay, 4 lines I have drawn. So that is something 00011011. So what is the input? 01. So 01 is input. In that sense, these pin will get enabled. Okay, it is getting enabled and all that other pins will be disabled. Okay, so that means now this complete row is in active state. Okay, now what I have given here 10. Okay, here also same thing, 0001 1011. Okay, so pins are there. Now 10 is given, so this is getting enabled. Okay, so now the common block will get enabled and the data is fetched from this address. Did you got it?
Yes, sir.
Okay, so it is very simple. Okay, so now this is called row decoder and this is called column decoder. Got it? So now how we need to design a decoder, what is the circuit for that? Okay, it is already given in the base paper, so let us see from the base paper itself. Okay, and that circuit we are designing in our software that is called Tanner EDA. Okay, Tanner EDA. Okay, it is a software. Okay, we will see the base paper from the Google itself. Method of low power address decoders for SRAM. So the method of low power high performance, okay, this is the base paper. And in this base paper, if you can see, OR and AND gates, okay, these are the basic gates which we need to design decoder, okay. So OR and AND gates are given here, okay. So like how it is OR gate is designed, how the AND gate is designed, we need to see once. And with that only, okay, so 14 FET and 15 FET, they have designed the decoder, okay. So let us see TGL. See, suppose if we are going to this one, TGL and, okay, AND gate, okay. So first figure, transmission gate logic, TGL, okay. So here it is given. Now how it is getting AND gate, we need to see once, okay. So with that you will get to know others also, okay. So just 1 minute, give me 1 minute. So this is the transmission gate, okay. Transmission gate logic AND gate, okay. So before that you should know the truth table, 00011011. So 0 0 0 and 1, this is the output for the AND gate, okay, A and B. So here there is like AB is replaced with XY and X into Y, okay. So uh, first you have to know which one is a PMOS, okay. See where you can see the bubble, okay, this is a bubble, so that is called PMOS, okay. And where there is no bubble, so that is called NMOS. So these are NMOS, these are NMOS, okay. So when PMOS will get activate, there are like gate. So when gate voltage is 0, PMOS is on, PMOS is on. When gate voltage is 1, PMOS is off, okay. And opposite of it, this is NMOS. When gate voltage is 1, PMOS is on, okay. When gate voltage is 0, NMOS will off, okay. NMOS off, that's it. So now see here, I will take some another pen so that, so VSS is nothing but ground. Is it visible, this pen? No, I think so. Color, okay. See here, I hope this is, so this is a ground in the sense 0, okay. So first let us try from these, okay, truth table, okay. So 1 0, I will take 1 0, okay. So what is 1? X is 1, so the here it is X, so I will take 1. Here it is X bar, you can see, so I will take 0, okay. And Y, what is Y? So Y is 0, okay. So 1, it is flowing to NMOS, see, okay, it is flowing to NMOS. In that sense, these NMOS is on, these NMOS is on. Now this 0, okay, now this 0 is flowing over here, okay, this is flowing over here. So it means 0 is flowing to this PMOS. In that sense, these PMOS is also on. Okay, so when both are on, so what is the y is 0, so it is flowing, y 0 voltage is flowing to the output, so that's why we'll get 1 0 is 0. Okay, let us try for some another one. So take another one, 1 1, output is 1. So x is 1, x bar will become 0. Got it? Y is 1. Then next, let us see. So when there is a 1, so gate voltage for this NMOS, this is on. So 0 gate voltage for this PMOS, this is also on. So when both are on, then directly these one is flowing to the output. That's it. Okay. This is how we will be getting the, means like the output of the NAND gate. Got it? Having any doubts in this?
No, sir.
So in the same way, you can see TGL OR gate and DVL AND gate, DVL OR gate. So DVL is called dual value logic. Here it is given. Transmission gate TGL. Okay. So both it has been given over here. Now what does it mean? Like transmission gate is nothing but, see, can you see this? Oh, 1 second here. There anything to highlight? Okay, 1 second. Okay. So see, when there is a combination of PMOS and NMOS in this way, okay, in this way, then it is called transmission gate logic. Okay, transmission gate logic. And in this dual value logic, you can see, so any of the input, like for the pull up network and pull down network. Okay, so x bar means like here it is given x negation. Okay, so see here, x negation and x negation, here also it is given x negation, x negation, so it is called dual valued logic. That's it, means two times you are taking the same value. Okay, so highlighting it is not possible here. Not there. Can you see my point? Means like, are you getting my point? Hello, are you getting my point?
Yes, sir.
So then next is just putting the values, like x is equal to 0 and y is equal to something. Okay, so you can means like verify these circuits if you want. Okay, but it will work. Okay, so now here if you can see that 14, so this is suppose 14T decoder. Okay, so see, three transistors are there, so this is a dual value. Okay, the next thing, it is a transmission gate, second one. Okay, the next, so this is a dual value logic. So transmission and dual value, so both they have taken. Okay, so and the last one, okay, D3. So this is a transmission gate logic. Okay, so 14 FET low power 2 to 4 decoder is designed with mixed logic. Okay, so 14 FET low power. Okay, so one is low power and another one is low power inverter. Okay, so inverter in the sense just we need to invert the inputs, that's it. Suppose if you are giving 1, so you need to give there 0. Okay, that's it. Okay, now that also I will let you know. So what does it mean? Okay, now the same thing 15 also will be done with the same thing, but extra transistor has been given. So this is the extra transistors they have used. Okay, here in the 15. Okay, so that is giving the high performance. Okay, that is giving a high performance. See, now one transistor we have used extra, it means the area is getting somewhat increased, but we are getting the high performance here. Okay, so that is a one means like what I can say, pros and cons. Okay, so that is an advantage. One extra transistors I am taking. Okay, then with that, so whatever 2 to 4 decoders we have designed. So with the 2 to 4 decoders, again 4 to 16 decoders can be designed. Okay, 3 to 8 and 4 to 16 again that can be designed. So here there is not clear information. So these are NOR gates and these are NAND gates they have taken. Okay, let us see, is there any clear information in the Google on that? Just I'm looking for that clear circuit diagram. Okay, Okay, so here it is given. So now you can see this is the NOR gates. Okay, so 4 to 16 decoders has been designed. So from this you can have a clear idea. Can you see my screen? Hello.
Yes, sir.
So see here. So this is the NAND gate. Okay. So this is one of the 2 to 4 decoder by using NAND gate. Okay. So inputs given A, B. Okay. Then next, this is another 2 to 4 decoder with NAND gate. Inputs given CD. Okay. So here there is a input AB and here there is a input CD. Okay. So how many inputs are there? 4 inputs. Okay. Now the output came from these. Okay. So A plus B, A plus B bar, A bar plus B. Okay. These outputs. Okay. Now it is going for these NOR gates. Okay. So you can see 16 NOR gates are there. So 4 inputs, 16 outputs we are getting from here. Okay. So what they are doing here? So these A plus B. Okay, these A plus B they are giving for the first 4 NOR gates. Okay, you can see first 4 NOR gates. A plus B is the common. A plus B, A plus B. Okay, so then next the other input for these NOR gate. Okay, so it is giving C plus D, C plus D bar, C bar plus D, and C bar D bar. Okay, if you can observe here, C plus D, C plus D bar, then next C bar plus D, and then next C bar D bar. Okay, so here we got the first 4 outputs. Okay, second what we'll do, A plus B bar is common for all the 4. Then next this is repeated. Okay, then next A bar plus B is common for the next 4 and this is repeated. Okay, then same thing. Okay, up to all the outputs we need to get. Okay, so like suppose can we see one of that, so how it is really happening. So this is the circuit. Okay, so here also same thing, just gates are exchanged, that's it. So now for observe here, A bar B bar, so there is an AND gate and so we will see here once. Okay, so A bar B bar NAND gate. Okay, so 4 NAND gates are there. A bar B, A B bar, A B. Same here, C bar D bar. Then next C bar D. Then next C D bar C D. Okay. So from that NAND gate. Okay. So from that NAND gate, what we will get here? A plus B given here. Okay. A plus B. Then next A bar plus B bar. See, directly we won't get A plus B. Okay. So NAND gate is something like this. A bar, B bar. If you give input, then it will be something like A bar dot B bar. Okay. So there is a dual value logic theorem. So like for that, when there is a bar, we will take off the bar and dot will be changed to plus and b bar. Okay, bar is there, so we will be changing it to directly normal one. So it becomes a plus b. Okay, in this way we need to minimize it. So minimization is given there. Okay, so that comes like Boolean algebra and all those things. So a plus b bar. Then next a bar plus b bar. Okay, then here also c plus d, c plus d bar, c bar plus d, c bar plus d bar. Okay, now suppose uh, how you will six means like 4 to 16 decoder will look like. It is something like this: d0, d1, d2, d3, d4,
Sir, I
d5.
think your screen
It is not okay.
isn't visible. Yes, sir.
Okay, so it is something like this: d5, d6, d7, d8, d9, d10, d11, d12, d13, d14, d15. Okay, so inputs are, it is starting from 0, 0, 0, 0 to 1, 1, 1, 1 inputs. Okay, so as it is not having that much space to write the inputs also, you just consider inputs will start from 0, 0 to 1, 1, 1. Okay, so total inputs are 16. Okay, and outputs are also 60. Input combinations are 16. Okay, input bits are 4, combinations are 16. Okay, so now suppose, okay, I will try it here. Okay, so it's better you can understand, otherwise d0, d1, d2, d3, d4, d5, d6, d7, d8, d9, d10, d11, d12, d13, d14, d15, d16, and here we will give something a b c d. Okay, a b c d. So starting from 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, double 0, 0, 1, 1, 1, sorry, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. So like that combinations. Okay, now in this output, how it will be? So 0, 0, 0 is in the sense 0th pin is enabled, d0 will enable, remaining all 16, sorry, all 15 will be 0. Okay, that's it. 0, 0, 0, 1. Then next, so only first pin d1. Okay, d1 is enabled, so others are totally 0. Okay, this is how it will work. So we will take first 4. Okay, to see from the circuit. Okay, means like once we see any of the one, so then you will be getting like an idea. Okay, now so like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0. Okay, that's it. So now ABCD. So what is that ABCD? We will write here ABCD combinations, and I am taking these four. Okay, 1, 0, 0, 0. Okay, and ABCD combinations are something 0, 0, 0, 0, 0, 0, 0. 1 second. 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Okay, so A, B, C, D. Okay, A is 0, B is 0. Okay, you can see. Now for this, for this 4 1, okay, 4 combinations, if you can see AB is common, so that's why in this AB is common. Okay, for the first 4 D0, D1, D2, D3. Okay, because AB is 0, 0, 0, 0. Okay, So, but CD is changing. 0 1 CD is changing. So see 0 0 0 1 1 0 1 1. Okay. So that's why what we have taken. So AB we have taken for one of the input for that NOR gate. Okay. So NOR gates we have taken something like this. 1, 2, 3, 4. So A plus B is common. So A plus B is common in the sense that is 0 0 0 0. So nothing but 0 itself. Okay. So 0. Not 0 0. No, you can say only 0. Okay. So first 4. Okay. First 4 NOR gates having one of the input is 0. Okay. Another. Okay. Another what we are having 0 0 0 1. So 0 0. Give here 0 0. Okay. What you are getting from that. Okay. So 0 bar is 1 1. So but output you are getting something like this. Okay. So whatever you are getting you have to write here. So now what is that you are getting? C plus D. C is 0 and D is 0. So you will be getting 0. Okay.
Sir, are you writing, sir? Okay,
Yeah,
okay. It's now visible, sir.
yeah. Okay. So 0 0 NOR gate 1. Okay. 0 0 NOR gate is 1. Then C plus D bar. So C is 0 plus D bar 0. Again it is I think 0. 1 second. 1 it becomes 1 and it becomes 1. So when there is a 1 1 2 NAND gate, so output is 0. Okay, that's clear. Then next, when there is a 1, when there is a 1 and another input is also 1, so 1 1 to NAND gate, that is NAND gate output 0 0 0 1 1 1 0. C bar 1 1. C bar D plus D bar. What is a C? C is 0 or with D bar, so it is also becoming 0. C bar plus D. So C bar is 0 D. 1 second, guys. Just wait. Okay, just wait for 5 minutes.
Please, sir.
Just wait. Hello, guys, are you there?
Yes, sir. Yes, sir.
Yeah, yeah. Sorry for the
Yes.
inconvenience.
Yes, sir. No problem.
Okay, so we are at this stage now. Okay, let us see what is this. Zero zero bar d bar. Okay, 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 okay. C bar, okay. C bar, and it is already given actually. Okay. So actually the thing is that once we just okay. So here it is 0 0 0 0 in the sense C input is 0 0 in the sense already it is a C bar. So we don't need to convert here. So it is a 0 itself. It is a 0 itself. Okay. So when we are giving 0 0 input to the NAND gate, okay, so what we are getting the output, so that is 1 here. Okay, that is 1. So that is nothing but the means like, so NAND gate truth table we have to know. So what is the NAND gate? 0 0 0 1 1 0 1 1. 0
One
0
one.
is 1, 0 1 is 1, 1 0 is 1, 1 1 is 0. Okay. Then next 0, C is 0 in the sense C bar it is given. So 0 1. So 0 1 NAND gate. Okay. So NAND gate again it is a 1 itself. Then next 1 0, again it is a 1 and 0 for the NAND gate 1. Then next 1 1, it is 0. Okay. So let us see OR gate. Okay. So what output we got here? 1 1 1 0. So C plus D. So 0 1 NOR gate. So 0 0 0 1 1 0 1 1. So 0 0 is 0 1 1 1 1 0 0 0. When there are both the inputs is 0, it is 1. Okay. So got it. Okay. Other are like, see, 0 1. Input is 0 1. So then it is a 0 itself. Input again 0 1 0. Again 0 1 0. Here there are inputs 0 0. So it is 1. Okay. So now these thing it is given as a D0, D1, D2, D3. Okay. In this way it is given. Got it. So D0 we got 1, D1, D2, D3. Like that we need to take. Okay. Got it. Did you got it, guys? Did you got it? Just we are just replacing that values. That's it. So if you not got it also, we'll see it last. Okay, because we need to see the design also. Okay, I will send you these thing also. This
Okay, sir.
whatever the circuit diagram is there. Once you try with that, okay. So the next thing, now once this is all done, so we are going for the so this is the software, and these are the designs. Okay, so 224 HP, 224 HPI, okay, and 224 LP, 224 LPI. So 224 HP. See, whatever in the base paper, so we have designed with the help of that. So now we'll see something about this software. See here, this is a Tanner EDA. So this is called S-Edit software. S-Edit is in the sense schematic edit. Okay. So whatever you are doing with the help of transistors, so that is called schematics. Okay. So like suppose I need to design something. Okay. So what we need to do? So we need to take a transistor. Suppose there are a NMOS transistor, PMOS transistor given here. So this is the NMOS. So just what we need to do is we need to click on this instance button. Okay, so and I'm just dragging my mouse in this black area. Okay, you can see. Okay, so just I'm placing anywhere, and you can place number of transistors here. Okay, so here we are having a wire, soldering point, connection point, all is given. Okay, so with the help of wire, what we will do, we will complete our circuit. Okay, so I'm just giving here example. Okay, so give the connections whatever you want. Okay, so in this misc you are having ground. Okay, so just click on instance, you can connect your ground here. Okay, so you are having VDD, so VDD in the sense power. Okay, so you can connect here. Okay, so then next input and output, see here, so there is an input port, click here and come to this black space. Okay, so for rotation R, you need to press R from the keyboard. So this is the input and this is the output. Okay, so this is how you need to connect. Okay, just I'm deleting it because it is already we have designed, so this is not needed actually. So now, so here are our circuits. So see, this is a input, this is a input. Okay, and where if there is a output, let us see function print voltage. Okay, now we need that outputs in the form of like waveforms. Okay, so we need to have print voltage. So this is the output, this is the print voltage I have given here. Okay, for inputs also we will give the print voltage. So A is the input, we will give the print voltage. Okay, in this way for all the outputs it has been given, and inputs are A and B. So A, where is the B? See here, B, for B also we have given at any one of the point. Okay, we need to give. Okay, so then next, these are the power source. So this is the power source. Okay, and where you get this power source? See here, go for the spice commands. Sorry, spice elements, voltage source. See here, here we are having some power sources, sine, AC. Okay, bit of 9. So we need to take one of, means like, see here, one thing is this one power source DC of 9. Why it is not getting? Okay, some mouse problem. See here. So this is the power source and this is the input source. So I have connected my A input, I have connected my B input. Okay, okay, got it. So next we have to go for the setup simulation. Okay, in the setup simulation you can see a library path, library file. Okay, so whatever here, okay, whatever it will be, okay, so you need to delete. Okay, so you need to delete from here. Now there is an option called browse option here. If your software is installed in this PC, so you need to go for these documents. In that you can find Tanner EDA. In that again you need to go inside Tanner tools. In that process, in that generic 250, in that generic 250 tech. So in that generic 250 nm.lib library file is available here. Okay, so you need to take from here. And at last give here space and capital TT, typical NMOS, typical PMOS. Okay, so click on OK. Now just you can see here start button. So you just click on this. So this is what our output is. Let us see how we got that output. Okay, see you can clearly see here. Suppose I am taking this one. This is the A input, this is the B input. Okay, so here there are the timing simulations, like see 0 to 10. Okay, so one input, 10 to 20 another input, 20 to 30 another input, and 30 to 40 another input. So two input combinations are like 4. Okay, so what are those? See here. So up to here one input, another input up to here, another input up to here, and see here. Now A B 0 0. Okay, so A is 0,
Zero one.
yeah, B is rising. Then next 1 0 1 1. Okay, now D naught, when there is a 0 0, D naught will be enabled, and remaining, see, remaining all are zeros. Okay, and 0 1, D naught is 0 and D1 will enable, and remaining all are 0. Got it? Then next 1 0. So this is 0, this is 0. So second pin is enable and 0. Then next 0 0 0 1. Did you got it? So these are the outputs. See, whenever we are writing the truth table, so we will write in the horizontal form, but in the waveforms we need to see it in the vertical form. Okay, got it? Did you got it? These all, these D0, D1, D2, D3 are our outputs. Got it, guys? Anyone having doubt in this?
Sir, once you repeat it.
See, uh, 1 second. 0 0 is the input. 0 0 is the input. So when both inputs are 0, so D naught pin will be enabled. Okay, So that's why D naught pin will be enabled and remaining all are 0. You can see remaining all 3 outputs are 0. Okay. When 0 1 is enabled, okay, so D1 pin will be enabled. D1 pin. Okay. So D1 pin is enabled now and remaining 3 whatever you are having that are 0. Okay. So then next 1 0. 1 0 is nothing but 0 0. Second pin is enabled 1 and this is also 0. Okay. So 1 1 0 0 0 and 1. And again one shortcut I will let you know. 0 0 in binary ante endi 0 0 ante nothing but decimal
Zero.
point. Okay na 0 1 0 1 binary lo
One.
decimal 1.
One.
Okay. So this is 2 kada, this is 3. Okay. So this 0 undi kada, so it is a 0, so that's why D0 pin is enabled. So it is a 1, that's why D1 pin is enabled. Okay. It is a 2, so that's why D2 pin is enabled. Okay. D2 pin is enabled. And it is a 3, that's why D3 pin is enabled. That's it. Remaining and is 0 ఉంటాయి. Okay. Got it? Did you got it, guys?
Yes, sir. Remaining 0. Okay, sir.
Yes, sir. You got it.
So now whatever 2 to 4 2 to 4 2 to 4 2 to 4 are given here, same output you will be getting. Okay. Some power and delay changes. Okay. అవుట్పుట్ సేమ్ ఉంటుంది. ఓకేనా, డికోడర్స్కి అవుట్పుట్ సేమ్ ఉంటుంది, బట్ పవర్ కాంబినేషన్స్ అవి కొంచెం డిఫరెంట్ ఉంటాయి. సో దట్ ఈస్ నౌ వాట్ వీ నీడ్ టు స్టడీ. ఓకే. సో 4 to 16 ఆల్సో చూడండి. For 4 to 16 outputs and 4 inputs are there. So if you can just see here also, delete చేయండి. Then you need to take generic 256 number. TT, click OK. సో చూడండి, ఎందుకంటే ఇన్పుట్స్ అంటే అవుట్పుట్స్ ఎక్కువ ఉంటాయి, సో కాబట్టి మనకు ఇలా వస్తుంది చూడండి. D1, సో all are getting enable at only one time. Okay. సో చూడండి, C input, so D0 1, remaining all are 0. See, remaining all over the time it is 0. Okay. So D10, so outputs jumbled గా వచ్చినాయి. ఓకే. సో మీన్స్ లైక్ ఇవి కరెక్టే మనకు. ఓకేనా, బట్ డోంట్ వరీ. సి D1. ఓకే. సో 1, remaining all time is 0. Then next 1 here 1, D3, D4, D5, D6, D7, D8, D9. Okay. Remaining all time is 0. Okay. D9. Then where is the D10? D10 is here. Okay. Then next D11, D12, D13, D14. Okay. Line. So here there is a one drawback that in waveforms ఎక్కువ ఉంటే మనం దాన్ని మనం చూడలేము. ఓకేనా. సో ఇలానే వస్తాయి, చిన్న చిన్నవి వస్తాయి. ఓకే. సో ఫర్ దట్ పర్పస్ వీ కెన్ టేక్ 4 first time, then next again we need to run, again 4 we need to see, again we need to run. So like that we need to do. Okay. So but output is correct. Okay. Now we need to jump over here. So 2 to 4 HP, setup simulation. Okay, you have done the setup simulation. Then next you need to see spice measure. So where is that spice measure? So ikkada spice measure ani undi. In that you need to see trans measure delay. Okay, so you have to take an instance here. Okay, in that instance, uh, what you need to take is, suppose once before taking that we need to just run here. Okay, 2 to 4 run చేద్దాం ఒకసారి. So run cheste. So how we are getting the output, we need to check once. So snipping tool, where is my snipping? So 0 0 0. Okay, ఏ ఇన్పుట్ అనేది ఇక్కడ వరకు కాన్స్టెంట్ ఉంది. ఓకేనా, సో బి ఇన్పుట్ అనుకోండి, ఇక్కడ 0 ఉంది, మళ్ళీ ఇది రైజ్ అవుతుంది. ఓకే, సో 0 నుంచి 1కి వెళ్తుంది. ఓకే, అట్ ద సేమ్ టైం D1 అవుట్పుట్ ఆల్సో 0 నుంచి 1 వెళ్తుంది. ఓకేనా, 0 నుంచి 1 వెళ్తుంది. సో మనం ఏమనుకుందామంటే డీలే దీనికి చెక్ చేద్దాం. ఇక బి ఇంకా D1. ఓకేనా, బి D1కి డీలే అనేది చెక్ చేద్దాం. సో ఫర్ దట్ పర్పస్ టేక్ ద ట్రాన్స్ మెజర్ డీలే. ఓకే, సో ఇక్కడ చూస్తే ఒకటేమో ఇక్కడ ఇన్పుట్ ఉంది, ఒకటేమో ఇక్కడ అవుట్పుట్ ఉంది. ఓకేనా, సో బి ఇన్పుట్ తీసుకుందాం. సో బి ఇన్పుట్ తీసుకుందాం, D1 అనేది అవుట్పుట్ తీసుకుందాం. సో D1 we need to take it as a output. Yes, taken. Okay, so just click here. Here there is a max voltage VPR is there, so you can do. So if you are not getting, I will let you know. Here at the right side VPR is there. Okay, so you just need to delete it, give here 5. That's it. Okay, then next go for the T spice. Open in T spice. సో ఇక్కడ కింద టీ స్పైస్ అనేది ఓపెన్ అవుతుంది. ఓకే, సో ఇన్ దిస్ you can see the second line. Okay, measure tran is there, no? So this second line you need to delete it off. Got it? Then next, so we are giving to B and we are means we are checking our output delay for this D1. Okay, so then next we are checking for the rise edge. So take out the fall from that. So this procedure video is there, and this is also getting reduced. Okay, means like recorded. Okay, so ME1 we need to change here delay. That's it. Okay, so you just need to and one thing we need to see power from here itself. You just give dot power. What is your input here? A. What is your inputs? A and B. So for A, what voltage source is given? VV1. VV1 dot power VV2. Okay, run here. So these already we have saw. Okay, so we know about this waveform. Just minimize it. So 1 second. So average power consumed. So this is our average power consumed. Okay, so power consumption, and then next delay. So 9.8 something delay. Okay, and then next MOSFETs. So 15 MOSFETs are there. Okay, so now MOSFETs is nothing but area. Power consumption, average power consumption is 4.7. Okay, so what we'll do, I will just copy this so that it will be better. Copy. So see here, these average power consumed 4.71 is there, and it is e to the power of -5. We need to change in a microwatts. Okay, na? So microwatts lo change cheste, so it will become 47.16. Okay, micro in the sense 10 to the power of -6, and this is 43.0. Okay, 43.07, 43.07 microwatts. Okay, so add it, divide by 2, that is your average power consumed, and this is the delay. Okay, got it? అర్థమైందా మీకు? హలో.
Yes, sir.
So ilane, so we have to check for all those ones. So already we have given here simulations and results lo ichina. Okay, so all those things we have given here, and just ఒకసారి check చేయండి. Okay, so if you are not getting, just let me know. Okay, so just you need to check from this reference video itself. Okay, so software install చేసుకున్నారా?
Yes, sir.
ఓకేనా? సో ఒకసారి మీరు అంటే నేను సురేష్ సార్కి పంపిస్తా ఇది, సో మీరు మీ దాంట్లో చెక్ చేసుకోవాలి. ఓకే, వాట్ ఇట్?
ఇప్పుడు సార్ ఈ క్లాస్ రికార్డింగ్ అది కూడా పంపిస్తారు సార్?
yes 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 yes.
Okay, sir.
So this is all about our project. Okay, so if you are having any doubts, you can call me or like message చేయండి, లేకపోతే సురేష్ సార్కి చెప్పండి, నేను ఆ రోజు ఏదైనా డౌట్స్ ఉంటే నేను తీసుకుంటాను. ఓకేనా?
Okay, sir. Okay.
దిస్ ఇస్ రికార్డెడ్, నేను పంపిస్తా ఈ రోజే వీడియో, మీ రికార్డెడ్ వీడియో 1 hour 70 minutes రికార్డెడ్ వీడియో. ఓకే, సో ఐఎమ్ జస్ట్ స్టాపింగ్ హియర్.